Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to show you how geometric invariant theory can be used to classify finite dimensional representations. And in so doing, show a very, very interesting relationship between geometry on one hand and algebra on the other hand. Okay, so to do so, I want to give a quick recap on Quivers. So if you don't know much about this, you can look at my video on Y modules and Quivers. And so the starting point, we have some sort of field that we want to work over. And what is a quiver? A quiver is just a directed graph, like one of the three that you see here. Okay, so directed means that each of these edges are actually arrows. There's a head and there's a tail. And what we can do is we can talk about representations of them. Okay, so in this case here, what's a representation? Well, in each of the cases, you replace each of the vertices, okay, the dots here, with a vector space. So here, this is a vector space, V. And each of the arrows will be a linear map from corresponding vector spaces. So here, it's just from this vector space V, this alpha x, this linear map is from the vector space V back to itself. And the key point is that this is strongly related, these representations, to modules over the path algebra. Okay, in fact, they are equivalent to modules over the path algebra, and in this case the path algebra here is just a polynomial ring in one variable. So just to remind ourselves what the path algebra is, it basically has a basis consisting of paths inside this graph. Of course, the only paths that you can have here, well, you can have the zero length path, which is just a point here, okay, and 1 times that will give you the identity here, okay, and then you can have the length n path where you just repeat xn times, and that's x to the n, okay, and that's the a basis vector for this thing here, and you multiply just by composition of paths. Okay, so that's how you get this path algebra here. Let's just quickly go through these other examples. Here you have 2 vertices, 2 arrows. So a representation of this quiver is just these 2 vector spaces and 2 linear maps between them. Okay. Here's the path algebra. Okay, so where does this path algebra come from? Okay, so for each of the 2 zero length paths, okay, the one at E and the one at F, they correspond to these diagonal idempotents. It's E with zeros elsewhere, and then the F with the zeros elsewhere. As for the length 1 paths, X and Y, they correspond to these upper right entries here. The X with zeros elsewhere and the Y with zeros elsewhere. And that's a basis for this path algebra. They're no longer length paths. And that's the path algebra, and you can check that it multiplies just as you would in a matrix, so this is a good representation for it. Finally, let's look at a slightly more interesting example. Here's this quiver here, a representation. You replace each of the 3 dots with vector spaces, and now you have 2 linear maps like this. Alpha x now goes from V0 to V1, and alpha y goes from 1 to 2. So similarly, since there are 3 dots, you have 3 diagonal idempotents corresponding to these diagonal entries here. You have 2 length 1 paths, X and Y, and they form the basis elements here, X with zeros elsewhere, Y with zeros elsewhere. But you also have a length 2 path, X times Y. So if you multiply this X with zeros elsewhere with a Y times the zeros elsewhere, you'll get this XY with zeros elsewhere here. Okay, so that's the path XY. There are no longer length paths, so remember in this path algebra, Y times X, since you can't compose in that order, is 0. Okay, so you get this XY, but YX is 0. And this matrix description, so basically it's just upper triangular matrices, okay, is the path algebra. And so representations of this, they correspond precisely to modules of this path algebra here. Okay, so what's the aim of this video? Well, one way to sum it up is as follows, okay? You look at these 2 examples here. Okay, so this is something that you study in your first linear algebra course, okay? Endomorphisms of a vector space. And what's the best way to study it? If you know some module theory, it turns out the best way to study it is to realize that any such linear endomorphism gives you a kx module, okay? Where x acts like this here. Okay, so the best way to study this, in fact, is to study kx modules using the fact that this is a principal ideal domain and the structure theory for finitely generated modules of a principal ideal domain. Okay, so what I want to do here is to generalize the correspondence that I've just sort of alluded to here. Okay, so in particular, if you look on this side, you look at kx modules which are d-dimensional. They'll So let's look at these up to isomorphism. So isomorphism classes of these, in fact. okay, they correspond to objects like this, okay, and up to isomorphisms you can replace V with K to the D, corresponding to D-dimensional, and you look at similarity classes of representations of this form, okay. So this is like when you want to look at linear algebra using the theory of Jordan canonical forms, you look at this, okay, and this is, if you want to look at it using the proof and the structure theory of principal ideal domains, sometimes it's good to look at it like this. So I want to generalize this correspondence from this situation here to both these situations and more generally, okay? And it's simple to see how it works if you just look at an example, okay, bearing this simple example in mind. Okay, so let's see how it works. And the most important thing is that we're going to use group actions, okay? So we want to set up invariant theory and we need a group action for that. So let's see how that works, okay? So let's suppose we're looking in this example C, we've got this quiver and a representation like that, and suppose it's finite dimensional, okay? In which case each of these V0, V1 and V2, we can pick a basis for them and then identify them with K to the D0, K to the D1 and K to the D2 for some triple D0, D1, D2. We'll put that into a vector, D vector, and we call that the dimension vector, okay? So it's not just one number, there are three because there are three vector spaces involved, okay? So it's clear to see that any finite dimensional representation of that quiver is isomorphic to one of this form. Okay, that's great. So let's look at the space of all of these. So in this case here, when we looked at linear endomorphisms of a single vector space, we took a basis for that to replace it with K to the D, and we look at the all the endomorphisms of that. So that's just D by D matrices, just square matrices of size D by D. Okay. So what's the analog here? Okay. So the analog here is the following. Okay. You want to look at basically the set of all of these. Okay. So what's involved here? You just have a linear map from K to the D0 to K to the D1. Well, that's just some alpha X, which is a D0 by D1 matrix. Okay. So here I've used the convention that I'm going to make these row vectors, and so these will act on the right. Okay, these matrices, these linear maps act on the right. And you also have the data of a second linear map from KD1 to KD2. Okay, so that's just a D1 by D2 matrix. So the set of all of these is just, well, it's just a Cartesian product of D0 times D1 matrices, the set of that, and D1 times by D2 matrices, the set of them. Okay, so geometrically, what is this object here? Okay, what is this object? Well, here you just have to give D0 by D1 scalars, which are the entries of this matrix. So it's just affine space of dimension D0, D1. And this here similarly is just affine space of dimension D1 times D2. So at the end of the day, when you take this Cartesian product, you just get some affine space, and the dimension of that affine space is the sum of those two dimensions, which is D0, D1 plus D1, D2. Okay? So this rep QD, the space that we want to look at, the space of all the data used to define this, okay, is precisely just some big affine space here. Okay, so that's the space that we want to look at, just like the space of square matrices we looked at in the theory of Jordan canonical forms. And now what we want to do is we want to look at something which is like the similarity classes. We want to look at a group action on that space. And where does that come from? Okay, so how can you get an isomorphic representation? Well, the key thing is that the only way you can get something isomorphic, okay, the way is you change bases. But now there are three vector spaces, so you can change the basis here, or here, or here, or any combination of those three. And that's our group of change of bases. Okay, so the group of change of bases is the following. We'll write it as GLD vector. So it's just the product of GLD0 plus GLD1 plus GLD2. Okay, so the point is that this will actually act on this space here. Okay, and let's see how that works. Okay, so let's pick a group element in this GLD. It's a triple of invertible linear matrices. Okay, invertible matrices G0, G1, G2. Okay, this is D0 by D0, D1 by D1, this is D2 by D2. And you act on a pair of matrices like this one here, okay? Act on something like that, okay? So how does that work? Well, we're going to change bases here, right, using G0. So this map is going to change. Firstly, you do the G0 inverse, and then you apply this map, alpha x, and then you've got to change a basis here as well, so you apply the G1, okay? And how does the alpha y change? What does the alpha y change to? Well, you change bases here, so you put a G1 inverse here, and then you do the alpha y to kt2, and then you change bases using G2 here, so you apply the G2 there. So in that way, you get new matrices here and here, possibly new matrices there and there, and it's quite easy to check that this actually gives a group action of GLD, the group of change of bases, on this representations of the quiver Q with dimension vector D. Okay? And just as we see here that similarity classes, okay, here, they correspond to GLD orbits of such D by D matrices of X here. They correspond to D-dimensional KX modules. Just as we see that, we find that here we have a similar situation occurring here. If we look at GLD orbits of pairs of matrices inside this rep QD, okay, they correspond precisely to the isomorphism classes of these objects and hence of these objects. Okay, they're precisely, in other words, the isomorphism classes of KQ modules of dimension vector D. Okay, so in this way we've achieved the aim of, if you want to classify all isomorphism classes of KQ modules, okay, so there are lots of them, so what you might want to do is you want to say, oh, let's fix the dimension vector first of these three vector spaces. Okay, so that's the dimension vector D, and then all you have to do is you form this rep QD and look at the GLD orbits of that. Okay, so we have exact generalization of that. And I hope you can see it's really easy to generalize the example C that I've got given here to example B or to any other quiver that you like. Okay, so of course it looks a little bit different and the notation gets a bit messy, but you can do it very easily. Okay, you set up, you replace each of the vector spaces in the representation with a number of copies of K. Okay, so you just pick a basis and then you have a similar change of basis, GL, whatever the new dimension vector is there, and it acts according to the recipe that I just described, but it may get a lot more complicated. Okay, so before finishing up here, I just want to make a quick remark, and that's very important, okay? So you'll note that scalar matrices, when you conjugate by a scalar, it of course doesn't do anything to this K to the D, this alpha X rather, because scalar matrices are central. Okay, and there's a similar notion that goes on here. Let's suppose you have what's called the delta is the diagonal copy of the scalars inside GLD. So what does that mean? So in GLD here we have triples. Okay, so this is D0 by D0, D1 by D1, D2 by D2. And now you just have some scalar alpha times the D0 by D0 identity here, and alpha times a D1 by D1 identity here, and alpha I, the D2 by D2 identity here, okay? Let's suppose we let that act, okay? So basically you have alpha here and alpha here, they cancel, because now since it's alpha times the identity, it commutes through, and they cancel. You have alpha here and alpha here, they cancel, okay? So the action of this subgroup is trivial on this rep QD. And since it's trivial on the rep QD, we can actually factor it out from this GLD. Okay, it's quite easy to see that it's a normal subgroup. It's normal because in fact it's central inside here. So it's a normal subgroup. And we take out the factor, we're going to call it PGL2D, okay, in analogy with the projective general linear group when this is just a natural number. Okay, so PGLD vector. And in fact, this acts on rep QD. Okay, so you have a quotient group that acts on rep QD. In the theory of Jordan canonical forms, you want to look at the space of similarity classes of square matrices. So we see now that we want to do the analogous thing here, which is to look at the space of GLD orbits of this rep QD. Now, one of the things that we also saw is that unfortunately, when you look at a space of orbits like this could be a very nasty object geometrically. It could be non-separated. In general, it's what you call a stack. It's not even a scheme. Okay, so one way to get a handle on this, or at least a big part of this, is to use semi-stability, which I introduced in a previous video. So that's a little bit of a complicated notion, but in this case, it works out to be something that's rather easy to get at. And that theory is due to King's. So I want to talk about King's theory of semi-stability in a particular simple example. So here I'm going to use what's called the canonical quiver here with the 2 dots and 2 arrows like that. And let's suppose we want to look at the specific case where the dimension vector is just 1 and 1. So you have a one-dimensional vector space here and here. So you, in other words, taking basis, you can have a representation of this form, k to k, and you just have 2 linear maps like that, which are of course just 1-by-1 matrices or scalars. Okay, so let's look at the setup that we had before. First, you have the group of change of bases. You can change bases here, so you can scale this by k cross, and this by k cross here. Okay, and there's a diagonal copy of k cross in there as well, which we have to factor out when we look at PGL of D. And when you work out what that is, essentially you can use this, for example, to cancel one of those. And at the end of the day, what you'll find is that you just have k cross acting either on here or on here, as you would like. Okay, so that's the group of change of bases. Let's look at the set of all these linear maps here, which is just given by 2 scalars, okay? So since it's given by 2 scalars, basically you just have k, 2 copies of k, or the affine plane. So in this case, this rep QD is a very nice geometric object. It's just the affine plane. Then you can work out how does this k cross act on this A2? Well, it's essentially just a scalar multiplication. And we've seen this sort of group action before. This is the group action that you use when you want to define the projective line, okay? The action of the group of scalars, the multiplicative group of the field on affine space. So in this case, it's the affine plane, so that gives you P1. Okay, so let's talk more generally. So let's leave this special example for a while and go to the more general setup of King's theory of semi-stability. So remember, this involves a choice of a semi-stability condition. And in this case, it's very easy to describe what that choice involves. What you do is you just pick some vector with integer entries. Okay, so it's z to the q. What does this q stand for? That's the quiver. It just means z to the number of vertices of q. So in this case here, you've got 2 vertices, z2. So this choice of theta is just a pair of integers. And you want an extra condition here that this theta dotted with the dimension vector is equal to 0. So I won't go into the details as to why this is the case, why you need this. It essentially corresponds to the fact that we've factored out by this diagonal copy of k cross the multiplicative group there. Okay, so that's a choice of a stability condition, and it's something that you just choose. Okay, so it will change the answer that you get depending on what this choice is. What this does for you is that you can now replace this rep QD with some open subset, which is the theta semi-stable subset. And the point is that in that case, what you might find is that a lot of the open orbits, which all got contracted down to a point before, and so you don't get anything interesting, now they can become closed in that open set, and so you can distinguish between them. Okay? And what's nice is that in this theory, you can actually find a modular interpretation for what this is. So in other words, you can define this subset in terms of the representations. So remember, each point inside here corresponds to a representation V, so it corresponds to something like this if you have this set up here. Okay, so just a pair of scalars. And in terms of the representation, you can say, what is that open subset? And what is that open subset? So they're the ones of the following form, okay? You pick a representation V like that, and what you're going to do is you can look at the ones that satisfy dagger. And to satisfy dagger, what you do is you look at all the sub-representations W inside that. And those sub-representations will have some dimension vector C. And you want to make sure that for that dimension vector C, when you dot it with theta, it's always non-positive. Okay, so if that holds, then it's inside this theta semi-stable open subset. Okay, so it's a bit of a strange notion when you first see it. So let's go to an example and see what it really means. Okay, so here we'll pick, we're back in example B to this canonical quiver. The D is 1, 1, and theta I'll pick to be 1 minus 1. When you take the dot product of that with this 1, 1, of course you get 1 minus 1 is 0. So it satisfies this condition here. Okay, so let's just see, well, which of these representations, like this, are semi-stable and which are not. Okay, so I claim that this one here, if you pick the alpha x and alpha y to be 0, that's not semi-stable. Okay, so how is it not semi-stable? It has to fail this condition here. So I'm going to come up with a sub-representation of dimension vector C where this inequality doesn't hold. And I claim the subrepresentation is this one here. Okay, you need a subspace of these, okay? So the subspace here, k, is just all of k, but you replace this k with 0, okay? And the key point is that since these are the 0 map, this will still map to this subspace. These two maps still map to the subspace. So this is a subrepresentation of this one here. And what is the dimension vector of this subrepresentation? Well, the dimension is 1 here and 0. C is 1 and 0. And if you take the dot product of this 1, 0 with this 1 minus 1, of course, you get just the 1 times the 1. That equals 1. And it doesn't satisfy this inequality. It's greater than 0. So since it fails this inequality, it is not semi-stable with respect to theta, not theta semi-stable. Okay. So suppose you have something which is not of this form. Okay, so you have a general representation, but now you're going to assume that either alpha x is non-zero or alpha y is non-zero. Okay. So of course you might ask, well, could you do a similar thing here? Okay, is this a subrepresentation? Well, if alpha x is non-zero, then k doesn't get mapped to 0, so that's not a subrepresentation. If alpha y is non-zero, then this k, you're multiplying by a non-zero number, so it doesn't get mapped to 0 either. So that's not a subrepresentation. It does have a subrepresentation. Of course, you can put both zeros here. And the only other one, if you put both zeros here, the dimension vector is 0, so this holds. And the only other one is if you have a 0 here and a k here. Okay, what's the dimension vector of that? Okay, so you have 0, 0 dimensional, 1 dimensional, so this c is 0, 1. Let's take the dot product of this with this 1 minus 1. Now the 1's in the other position, you'll pick up the minus 1. And this is less than or equal to 0. So for both subrepresentations, okay, this one and the 0, you'll get this non-positive quantity, non-positive dot product here. So in fact, it is theta semi-stable. Okay, so we've worked out semi-stability in this instance here. Okay, this example. Okay, so let's look at the quotient. Okay, so what do you have? So let's look at rep QD, the theta semi-stable part, modulo this GLD. In fact, we'll look at PGLD. Okay, so it will turn out to be the same, but let's just put that in there. PGLD. So what is this theta semi-stable part? Well, the only thing that was not theta semi-stable is 0, 0. So this rip QD is just this pair of numbers, so it's affine plane, A2, and you just remove the 0, 0, the origin from there. And what is this PGLD? The PGLD is just the multiplicative group K cross or GM, and it acts by scalars on this. And of course, what is this object here? Of course, this is a familiar algebra geometric object. It's just a projective line. Okay. So it turns out, quite interestingly, that in this case here, if you want to try to classify representations of this, what do you get? Well, you've thrown out, in this case here, the 0, 0, so there's one extra that you have thrown out, okay? That's its own orbit. But that orbit is an enclosure of all these other ones, and all these other ones are parametrized by points on the projective line. Okay, so you have a projective line of them. Okay, if you want to think of this whole object in this case here, you have, in this theta semi-stable part, you have a projective line of them. Of course, when you throw this point in, all these are actually, when you close them up, they contain this point here. Okay, so it's the whole object is quite complicated, but here what you get is you get a nice projective line. And what's really interesting about the mathematics here is that here you have a very algebraic problem. Okay, you're just classifying representations of this quiver. Okay, which also modules over some algebra. So in this case here, you can just even phrase it in terms of linear algebra. Okay, you want to look at linear maps from K to K, 2 of them. Okay, and you want to look at isomorphism classes of that. It's purely algebraic, and what you get out of that is some very interesting geometric object here, and that shows that there's an interesting interplay between algebra on the one hand and geometry on the other. And in fact, it goes much, much further than this, and there are lots of things that I can tell you about this, but I want to tell you just this one extremely interesting theorem due to balancing, which tells you an extra connection between this projective line and also representations of this Kronecker quiver. Okay, Suppose now you look at indecomposable representations of this quiver here. So representations look like this. You can look at these in terms of modules over the path algebra of this canonical quiver. We can talk about indecomposability. And of course, it's nice to know what they are, okay? Usually in module theory, that's what you want to do when you look especially at finite dimensional representations, is compute the indecomposable ones. And it turns out that you can describe this in terms of this geometric object P1. It turns out to be those representations correspond precisely to the indecomposable coherent sheaves on P1. So in this way, we find some extremely interesting and sophisticated connection between the projective line and the algebra of the canonical quiver. I hope you enjoyed this adventure in pure mathematics.